everyone, welcome back to News Chem Corner. In last episode, we explored atom, their structure, properties, and isotope, ions, everything. If you haven't seen it, first please check it out. That I'm providing the link here and the full playlist. In this video, we are going some deeper into it, like electronic structure, electronic configuration of an atom. This is the basic of all the chemical reaction, all the chemical properties, everything. So electronic configuration is highly crucial in field of chemistry. So if you are doing honors chemistry, you can also use this video. Let's get started. Electronic configuration. What do you mean by electronic configuration? It is the arrangement of electron in an atom, right? Because we know that atom is composed of proton, neutron and electron, in which protons and neutrons are situated at the center of an atom. We are called it as nucleus, and electrons are revolving around the nucleus. Okay, so how they were arranged, that is we are going to study. Okay, that is what you mean by electronic configuration, right? Okay, let's start the electronic configuration. Basically speaking, electrons are arranged in this kind of different orbits. So you can see surrounding nucleus there are different orbits are there, like our planetary system. So these orbits are main energy shell. See in this figure you can see a more clear picture, right? See the positive nucleus, and then there is different orbits. Each orbit is designated like n is equal to 1, n is equal to 2, 3, like that. So these are the different energy levels. Okay, do you understand? Electrons are in different energy level. Okay, these are called orbits. So which orbit is very lowest energy level? Ah, the an orbit which is closer to the nucleus will be the lowest energy level, because they contain nucleus like positive charge, protons. So that will attract electron, right? So the what electron close to the nucleus will have a more stable what position. So that's why we are telling energy will be lower for n is equal to 1. So as n increases, energy also increases. Correct? Whatever it is. Anyway, electrons you can see in orbits. These orbits, so orbits are n is equal to 1, 2, 3, like that. Different orbits are available where you can see electrons. Okay. Then that's all. Electron you can see in this kind of orbits. That's all. Ah, no. These orbits are again divided into some sub-level. So that is called a subshell. Subshells are designated like S, P, D, F. But the thing is, all the subshell is not available for all orbit. For example, first orbit contain only one subshell, which is S. So two contain two subshell. So what are them? S and P. Okay. So in order to distinguish this oneness and like one subshell and the second orbit subshell, you can write oneness and this one as 2s. So the coefficient represent the main energy level. Okay. So this one is 2p. Clear? So 3 contain how many subshells? Definitely 3 subshell. Okay. Yes, 3p, 3d, and definitely 4 contain 4 subshell. What are them? 4s, 4p, 4d, 4f. And what about 5? Fifth energy level contain how many subshell? Is it only SPDF? You may heard only about SPDF, but actually there are more. So 5 contain definitely is 5 subshell G. G is actually the next subshell. Okay, but so far we have only 118 elements. So we have only maximum electrons are 118 electrons, right? So that many electrons will fit it in these kind of 4 subshell. So we use only this 4 orbit, the 4 subshell. Okay, in order to accommodate all of our electrons, right? If we require more, yeah, definitely the next subshell you can include. Okay, right. Then the subshell is also again divided into some sublevel. Okay, so sublevel of subshell is what we called orbital. Okay, be careful, it's not orbit but orbital. So first main energy level is orbital, and second orbit are divided into subshell, and subshell is again divided into orbital. So what are the orbital? How they were designated? They were not designated, but you can just use the box. Okay, so like this kind of representation. The main thing is it's just like an odd number. All the s is divided into one orbital. Okay, so one s you can just show like this. Clear? And not only one s, all the s. So 2s is also like one box. 3s is also like one box. Okay. Then, as I told you, it's odd number, which means p is divided into three orbitals. So you can represent like a three box, like this. Okay. Oneness is just s. All the s is just one box. P means three boxes are there, and then 2p or 3p, whatever it is, what three boxes are there for p orbital, and d how many? It's odd number, right? So the next one is 1 3 5. So d is divided into 5 orbital, and f is divided into 7 orbitals. Okay, 4 5 1 2 3 4 5 6, and one more. Okay, so what are the thing? The main energy level is there, 1 2 3, like that. So what are the thing? 1, and 1 contain one sub level, so 1s, right? I can show in color. Mm. So in effect, what are the energy level, or where you can find electron? Okay, main energy level 1, and they have one subshell 1s, and the second energy level is 2, which have two subshell, which is 2s and 2p, right? And 3 have three subshell, which is 3s 3p 3d. And what are the orbitals? 1s contain one box, 2s contain again all the x contain one box, and 2p contain three box, and 3d contain, or all the d contain five box. Okay, like orbital. And 4f contain, all the f contain seven boxes. Okay, 4 5 6 7. Okay, okay, that's the uh, positions where you can find maximum electron density. Okay, these are the position electron want to fill. Okay, then now the question is, suppose sodium when you are taking, it contain 10 electron. So will all the 10 electron sit it in the oneness orbital? Ah, there are some rules and regulations. Okay, so electronic configuration. These are the position where you can find the maximum electron density, and the others, the three law will tell how this electron have to be filled. Okay, in these orbitals. What are the rules? The first rule is Aufbau Principle. According to Aufbau Principle, electrons are filled in the atomic orbitals in the increasing order of energy level. Okay, so what are the energy level? We have oneness. Okay, and then which is the next energy level? So as I told you, as n increases, energy is also increases. So which is the lowest energy level? Yes, n value lower means oneness. So oneness is the lowest energy level. So first electron will fill into the oneness orbital. If oneness capacity is over, then it will go to the next filling energy level, which is next energy level. What is that one? 2s. Okay. After that, 2p is there. After that, 3s is there, right? One contain one orbital, one subshell, two contain two, and three contain three. So after 3s, then 3p. You may think it is 3d, but actually no. Okay, before filling 3d, it's actually 4s. After that, only 3d. Why? Because this subshell also have an effect. Okay, so what we are telling is, only we are looking into what n value, like orbit energy, main energy level, right? As n increases, generally energy increases, but subshell also have some effect. Due to that, 3d will be comes only after 4s. Okay, 3d have slightly higher energy than 4s. So while you filling electron, First, you have to fill 1s, then 2s, then 2p, then 3s, then 3p before 3d 4s is there. Just have to study like that much. Okay, because you don't want to bother about this order. All this order you can quickly write by use of a periodic table. So now you don't want to intimidate anything. Okay, so this order I will tell how to remember this order. Actually, you don't want to memorize this order. Okay, just understand that this is the principle. Like Aufbau principle means electron has to be arranged in order of increasing energy level, which means 1s is the lowest energy level, and then 2s 2p, then 3s 3p before 3d 4s is there. Just understand that much. I will tell the more details. Okay. Right. So see the Aufbau principle. See like the in this diagram it is also clear. 1s and then 2s 2p. So we can write like 1 n is equal to 1 have only one subshell 1s. Okay. 2 have 2 subshell 2s 2p and 3 have 3 subshell 3p 3s 3p 3d and see 4s 4p 4d 4f and 5 as I told you actually 5g is also there but now we are not used. Okay. And then what happened? After 1s see the arrow mark, then 2s and then see the zigzag arrow mark, right? 3s and 3p, so see the arrow mark is actually leading to 4s. Okay, that's the easy way, like one of the method you can memorize, but no need. I'm again and again, no need even this order. Okay, just understand that principle, and that's why we are giving electron before 3d for us. Okay, don't want to bother about the order, I will tell. Okay, so the next principle is Pauli's exclusion principle. Pauli's exclusion principle, the result, actually Pauli's exclusion principle is something other, but don't want to look at that one. You can just think about the resultant of the Pauli's exclusion principle. Okay, because actual principle is related to quantum numbers. We don't want to do that one. Just the result. Result of Pauli's exclusion principle is actually what? Maximum number of electron in an orbital. Be careful, it's not orbit. Orbital is 2. Okay, which means all the s have how many orbital? One orbital. So how many electron they can accommodate? Maximum electron in an s subshell. Totally s subshell contain 2 electrons. So you can represent the electron like a arrow mark, half header or full header, no issue. If one arrow mark is at the like for what top end and the other one should be downward. Okay, right. And p have how many orbits? Orbital. P have 3 orbital. So each orbital can accommodate 2. So one is upward and the other one is downward. One is upward, other one is downward. Upward, downward. So see, maximum electrons in a p subshell is 6. Do you understand? Each orbital can accommodate 2. That is Pauli's exclusion. So S subshell capacity is 6 for P. Okay. Then what about D? D contained 5. So it's a odd number 1, 3 and 5. So definitely 5 contained 5 times 2. So 10 electron they can accommodate. Okay. And then what about F? F is 7. 7 orbital is there. So each one can accommodate 2. So 14 electron. So subshell as a whole, you can electron can accommodate is 2, 6, 10, 40. Okay. For example, if I am writing oxygen, 8 is the atomic number. So 8 electrons are there. So what are the rule? First, electron will go to the lowest energy level, which is 1s. How many electron they can accommodate? 2 electron. Correct. So I can write 1s and this superscript 2 means the number of electron. This one, the coefficient 1 means the energy level, right? This is our n value and this is our subshell and this one is the number of electron. Okay, right. So 1s2 and then electron will go to the 2s2, right? Electron will go to the 2s2 and then electron will go to the 2p and how many electrons? They can accommodate maximum 6 electron but see already we fill 4 electron and the remaining 4 electron will fit into the 2p. So this is the way of writing electronic configuration. Okay. Right. And actually, there is a third rule. This rule is also needed. Hund's rule. So what about Hund's rule? It says that the degenerate orbitals. For degenerate orbitals, lowest energy is attained when the number of electrons having the same spin is maximized. Okay. What do you mean by degenerate orbital? See, in top case, in about thing like oxygen 8, we represent like this. The same you can represent orbital notation. Orbital notation means what is orbit? Like a box like notation. Okay. So 1s2 I can represent like a one box with a 2 electron. Okay. One is upward arrow and the other one is downward arrow. Okay. And 2s2 is also I can represent like this. Correct. And 2p4. How do I represent 2p4? You know, p have 3 orbital. So the same 2 like 2p have 3 orbital. That is what you mean by degenerate orbital. Same energy orbital is what we call degenerate, which means all the p orbitals are degenerate. All the d orbital like their own 3d means all these 3d orbitals are what? Are degenerate. All these f orbital. Do not think 3d and 4d are same energy. That's not I'm telling. D orbital themselves, it's actually same energy. Okay, 1, 2, 3, 4, 5. Okay, so all these three orbitals are same energy. That is what you mean by degenerate orbitals. So in your degenerate orbital, how this how we represent the electrons? See, 4 electrons are there. You can have two way of notation. Like you can write 2 here and 2 here. This is one way of notation. And the other one is suppose 1, 2, 3, and this is 4. Correct? Both of them representing 2p4. So what do you think? Which one is correct? There we are using Hund's rule. According to Hund's rule, this notation is wrong. Okay, so that's why they were telling in for degenerate orbital, lowest energy is attained when the number of electron having the same spin is maximized. Okay, or we can say pairing. Pairing means second electron is also in the same orbital. Pairing can take place only after single occupation. Okay, so here suppose we are doing d5, d5. So 3d5 maybe. Okay, so first you have to draw orbital. Only this is needed only for what? Orbital notation. Okay, so 5 orbitals are there. Correct. So d5. First, what's the thing? Pairing. Pairing means the second electron is also in the same orbital. Pairing can take place only after single occupation. So this is d5. This one is correct. Otherwise, you can't write 3, 4, 5. You can't write like 1, 2, like 2, 4, and 5. This will be wrong. That is Hund's rule. But this is only applicable while you're writing this orbital notation. Otherwise, 1s2, 2s2, 2p, 4 like this kind of notation. Like see the thing. In this way, while you're writing, we are not using Hund's rule. Got it? Okay. Now you tell me, how do you write sodium? Sodium configuration. See, I'm giving the what? The atomic number 11. So if atomic number is 11, how do you represent? 1s2, right? The first energy level is 1s2, and then 2s2, and then 2p6, and yeah, 3s1, right? Because 10 electron, and this is the 11th electron. Okay. If it's so, what to do with the lead? Pb contain 82. 82 is the atomic number. 82 atomic number means 82 electrons are there. How do you write 82 electron? Right. Like, is it possible like 1s2, 2s2, 2p6, and then maybe up to the order 3s2, 3p6, and then you may be familiar like before 3d, what I told, 4s2 is there, and then 3d, 10 is there. Why 3d10? Because S can accommodate maximum 2 electron, P can accommodate maximum 6 electron because 3 orbital, D can accommodate 5 orbitals, so 10 electrons. And F 7 orbital, 7 times 2, 14 electrons are there. Okay, so 3d10, and you know, after that the order is it. I told you, I told you you do not want to memorize this order because we can use the periodic table. Okay, so it's very hard to do PB like these, correct? We want to memorize all these things, but I told you there is another way. Okay, now I can see how we can memorize or how we can get all this order. Okay, I'm guaranteed to do to you, we don't want to memorize or we want to not want to study this order because we have periodic table. So let's see how to do with the periodic table. Okay, so by using a periodic table, we can we can write the electronic configuration within second. Okay, let's see how it is, and after that we can complete the LED configuration. Okay, so the main thing is periodic table is divided into four categories, four blocks, you know. So the first two groups is called S block, and the 13 to 18 is what we called P block. Okay, and the middle block is what we called D block, and the bottom block is what we called F block. Okay, so what are them? I'm just erasing the slide. We can see after this. So first one, this is S block. S block, and this is P block. So S block and P block, what is the principle? I can use a principle. What is the principle? Period number is equal to N. Okay. And the D block is what we called the period, the principle is period number minus 1 is our n value. So what is this principle? What it means? I will tell. And see, what about the F block? F block, the principle is what? Period number minus 2 is our n value. So what does it mean? For example, I'm again taking sodium. So sodium, what we already done, 1s2, it's 11 only, so it's easy. 1s2, 2s2, 2p6, and 3s1 we were done. Okay, so how do you write the electronic configuration? By using this periodic table. Okay, so let's see the sodium. Did you locate the sodium? This is our sodium. So first step, locate the last noble gas. Okay, what do you mean by noble gas? This 18th group is what we call noble gas. So what's the first step? Ah, the last noble gas. Locate the last noble gas. So see, what is the last noble gas? You can't take argon because argon is the not the last noble gas, right? When we think about sodium, the previous noble gas, the last noble gas is neon, right? When we think about sodium, see, sodium is 11, so the previous noble gas is neon. Okay, so neon you can write like in a bracket, square bracket. So while you write neon in square bracket, which means you are already represented the 10 electron because neon is 10, right? Then what is the remaining? Okay, after neon, so you are already represented 10 electron, then one more electron is there. That electron will go to which orbital? That is the doubt, right? For that, you can use this kind of principle. Okay, so what does it mean? After neon, see, you need sodium, so you are dealing with a S block. First you have to locate the block, S block. If it's S block, what is the principle? Period number is equal to N. So what is the principle? Sorry, what is the period number? See, the sodium is in 1 2 3 period, so 3 is our N value, so it is 3, and the block is S, so it is 3s. And see, 3s and first element, like first group. Okay, so 3s2, 3s1 will be the sodium. So sodium will be Ne in square bracket and then 3s1. Okay, maybe you didn't get. So we can do one more example. For example, aluminum. Let's see aluminum. So see, locate the aluminum in periodic table. This is our aluminum. Again, first step, locate the previous noble gas, which is again neon. And then, so neon you can write, I can write here. So neon, neon you can write it in the square bracket, and then The next filling energy level is what? After neon, you are dealing with a S block first. In order to meet aluminum, you are dealing with the S block first. So S block, period number. So 3. So 3S, you are completing the S block, so 3S2. And then you are dealing with what? There is no D block elements in between them, right? After 12, this is the continuation. So then you are dealing with the P block. So which P? 3P, because period number. Again, the rule is same. 3S2 and then the first P block. So 3P1. Got it? Once again, what about germanium? See the germanium. How do you do with the germanium? The previous noble gas this time is argon, right? So you can write argon. You can write argon in square bracket, and then which is the next filling energy level. In order to meet argon, sorry, in order to meet germanium, you have to first deal with the S block. Which S block? This time period number is 4, so 4s2. And then see, you have to deal with the D block elements. So D block element, what is the principle? Period number minus 1. So it is not 4D, it is 4 is the period number. 4 minus 1, 3. So 3D. Okay, so first 4s2, and then 3D 10, and then again you are dealing with the C. You are dealing with the P block. So again principle changed, period number. So 4. 4 is the period number. So 4. P is the thing. Okay, then see, germanium is in the second group. Second group of P block. So 4P2. Okay, so this is the way of doing the configuration. So see, we are used to the thing. For us is the first one and then 3D. Without knowing that one, we just like we didn't bother about these things, right? We just look at the periodic table and we wrote this one. Okay, we didn't memorize any order, correct? So that's why the periodic table is it's actually you can get all the order. See, once again, can you look at the periodic table? This is what's the thing? S block. So first, this is oneness, right? Helium is also actually have to be here, right? Helium is an exceptional case because it's a noble gas. We are situating helium there. Okay. Otherwise, just think about the order. This is period number. So oneness, oneness 1, oneness 2. Okay. Then see the next one, 2s2, and then see 2p. This is 2p, and then 3s. Okay. Can you able to get the order like 3s? See the energy level order is this one. So whole energy level order, that the what I'm telling, that order energy level lower to higher energy level order you can get by from the periodic table. Okay, so see, this is 3s and then 3p. So see, after 3p, it's not 3D, it's 4s, and then 3D, and then again 4p, and then see 4D, before 4D, before 4f, 5s is there, and then 4D, then 5p, again 6s, correct? Again 6s, and then uh, the what 5D, and see there is a gap 57, and this is not 72, sorry, this is not 58. So what's the thing? The remaining is situated at the bottom. So actually after 5D1, the electron will fit it in the period number minus 2, which means 6 is the period. Because it's a continuation of sixth period, right? So 6 minus 2, it's 4f. So this one is 4f and this one is 5f. Clear? So after 5D, 4f will going to fit, and then complete the 5D, and then 6p and 7s, and like that, all the order you can get it. So that's it. Now you tell me, how do you do with the lead? So let's do with the lead. Okay, so first you have to allocate the previous noble gas, which is xenon. Okay, so we can write xenon at the square bracket, and then you are dealing with the 6s. Okay, so I can write here lead, right? So xenon in square bracket, and then 6s 2, and then see the thing, you are dealing with a D block, but D block, what I told, period number minus 1. So 5D is the thing. So 5D and all the D block is complete. So 5D 10 is there because 10. See 10 5D 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Correct? So that's why 5D 10. And then can we directly do to the P? Because we missed something. See here some elements are there. As I told you, one electron 5D1 is actually filled and then they will fill 4 of, because see 4 of electron have to fill. Okay, so you can write after 5D. Now if you don't want to write like 5D1 and 4 of 14 and then again 5D9 like that, not want to write, you can just write 5D10 and after that you can write 4 of, no issue, 4 of 14 and then we already done with the D block and then it will go to the 6P. So 6P and see lead is this one. So 6P 2. Got it? So in this way you can easily write any configuration. Okay, so that's why I told you don't want to memorize any like any order, just want to deal with this one SPDF like that. The blocks are there and yeah, principle S and P same principle, period number is equal to N, D means period number minus 1 and F means period number minus 2. Okay, that's all. Now let me see, what about the electronic configuration of ion? For example, titanium 2 plus. Okay, so where is titanium? You can see this is our titanium. Okay, so again argon we are writing because that's the previous noble gas, and then what is titanium? Just titanium, and then 4s2 and then 3d2. Okay, then so titanium is what? First I'm just writing titanium, argon, and then 4s2 and 3d2. Okay, so this is called a noble gas notation. Okay, this is the our normal electronic configuration, but simplified electronic configuration is what we call noble gas notation. Okay, both the case simplified electronic, condensed electronic configuration, or otherwise called all these things are noble gas configuration. Okay, so this is the normal electronic configuration. Okay, or condensed, because the normal electronic configuration is usually we are writing like condensed form. They don't want to be particularly specific. Every time we are used for convenience this condensed form. Okay, so titanium is this one. Okay, then what about titanium 2 plus? Titanium 2 plus means it's a cation. What is cation? How cations are formed? By giving electron. As we told, donation is a positive thing. So electrons are donated. How many electrons are donated? 2 electrons are donated. So how do I write the cations electronic configuration? Argon and 4s2. Is it correct? There is a problem. See, do not write argon 4s2. From where the electron has to lose? That's the problem. Okay, from where the electron have to lost? See, always electron have to lose from the valence energy level. Valence energy level means highest energy, highest n value. Okay, always it is from valence shell. Valence shell means highest. Okay, highest n value. So which is the highest n value? 4 is the highest energy. Okay, highest energy like highest to n value. So electron have to lost from the 4s. So argon 3d2 is there, but 4s electron have to lose. Okay, be careful with these things. Always electron have to lose from this valence or highest n value. Okay, that's it. Now there is a small point, anomalous configuration. What do you mean by anomalous configuration? For example, chromium. How do you write chromium electronic configuration? So see the chromium. This is our chromium. So the lowest, like the previous noble gas is argon, and so argon, and the next filling energy level is C 4s, 4s2, and 3d 1, 2, 3, 4. Correct? So 4s2 and 3d1 is the 3d4, right? 3d4 is actually the chromium, right? Like that we are writing from the um, periodic table. But actually there is a twist. What is the twist means? You know 3d is 3d. What is the 3d? 1, 2, the orbital notation is what? 1, 2, 3, 4, right? 1, 2, 3, 4, and D5 actually the thing. Like D maximum electron is 5, correct? So if D5, if it were a D5, they can get a more stability. Okay, what I'm telling, there is an extra stability for full-filled and half-filled orbitals. Okay, for full-filled and half-filled means S, full-filled means 2, half-filled means S1. P full-filled means, completely filled means P6, and half-filled means P3. D10 and D5. Similarly, F17 and F47. These have some extra stability. So for getting this extra stable configuration, what they will do, this forest electron will jump it into the 3D shell. So what should be the configuration? Argon 4s1 and 3d5. Why? Because in order to make a more stable configuration, extra stable configuration. Okay, but be careful, even S2, S1, P6, P3 have this extra stability. This electron jumping is not seen. Okay, this anomalous configuration is only you can found with a D and F block. Okay, very careful. You can have the power to jump this electron only for D block and F block. Okay, so for example, copper while you writing, again it's argon. So you can see the copper, this is copper, right? Copper, argon is there, and see, then the next filling energy level is 4s, and then it is 3d9. Okay, 4s to 3d9 is the thing. 4s to 3d9, maybe the first one, but the problem is what? This is wrong. What is the actual configuration? This electron will jump to here. Why? In order to make D10. Okay, got it? Only this jumping you can see with the D block and F block. So this is 3 4s1. Okay, this will be the correct one. This is what you mean by anomalous configuration, right? Not normal, right? So this anomalous configuration you can see with this one. See, there is no D4 configuration. Clear? There is no D4 configuration. Only D5, like 4s2 D4 is not there, but 4s1 D5. Similarly, 4s2 D like or 3D9 is not there, D9 is not there. One electron will jump to this one. Okay. Similarly, see the F block. This is F1, this is F2, F3, F4, F5, F6 will be not there. That will be F7. One electron is jumped there. And here also F4 13 will not be there. It will look like F14. Okay. So these group have this kind of anomalous configuration. Got it? That's all the electronic configuration. And that's it for today's video. If you found this helpful, give it a thumbs up and share it. Subscribe to Anomalous Chem Corner for more videos. I will come back with another basic topic in next video. Bye.